In this video, I provide a short overview of three notational systems: decimal, binary, and hexadecimal. The decimal system is base 10 and includes the numbers 0 through 9. In this example, the number 4 is in what we will call the ones column, 3's the tens column, 2 the hundreds column, and 1 the thousands column. Each place value going from right to left corresponds with 10 to the exponent of 0, 10 to the exponent of 1, 10 to the exponent of 2, and 10 to the exponent of 3. If we were to calculate the values, we would multiply 4 times 1, which is 4, 3 times 10, which is 30, 2 times 100, which is 200, and 1 times 1,000, which is 1,000, for a total of 1,234. The binary system works in a similar way, except instead of base 10, it's base 2. In other words, instead of 0 through 9, we only have 1s and 0s. Since the binary system is base 2, we have 2 to the exponent of 0, 2 to the exponent of 1, 2 to the exponent of 2, and 2 to the exponent of 3. The 2's take the place of the 10's place. The 0 exponent is always equal to 1. 2 to the exponent of 1 is 2 times 1, or 2. 2 to the exponent of 2 is 2 times 2, or 4. And 2 to the exponent of 3 is 2 times 2 times 2, or 8. If we were to extend this to 8 place values, we would have 2 to the exponent of 4, which is 16, 2 to the exponent of 5, which is 32, 2 to the exponent of 6, which is 64, and 2 to the exponent of 7, which is 128. In computer terms, each place value is equal to 1 bit. 8 bits are equal to 1 byte. In the decimal system, the 10 place values make sense from a numerical standpoint, but how do we make calculations when all you have are 1s and 0s? Computer systems are based on wires and switches that turn on and off. The 1s and 0s represent these on and off states. If we were to convert binary to decimal, we would only count the 1s, which represent the on states, and we would not count the 0s because they represent the off states. In this example, we would multiply 128 times 1, which is 128, 16 times 1, which is 16, 8 times 1, which is 8, and 1 times 1, which is 1. This would give us the decimal value of 153. In contrast to the decimal system, which is base 10, and the binary system, which is base 2, the hexadecimal system is base 16. I know what you're thinking. If our single-digit number system only includes 0 through 9, how do we represent 16? The hexadecimal notational system is different from binary and decimal because it can also represent letters. For example, after 9, 10 becomes A, 11 becomes B, 12 becomes C, 13 becomes D, 14 becomes E, and 15 becomes F. The numbers and letters combined equal 16 place values. Let's go back to our chart example. Going from right to left, replacing 10s and 2s with 16s, 16 to the exponent of 0 is 1, 16 to the exponent of 1, or 16 times 1 is 16, 16 to the exponent of 2, or 16 times 16 is 256, and 16 to the exponent of 3, or 16 times 16 times 16 is 4,096. In this example, let's convert 4D to decimal. D, which is 13 in hexadecimal, times 1 is 13. 4 times 16 is 64. The decimal value of 4D is 77. You may have noticed hexadecimals in some of your computer programs. For example, color swatches in the standard graphical user interfaces are actually hex colors. For example, a shade of blue is represented by the hex number 004D81, or 19,841 in decimal, and these 1s and 0s in binary. Let's try to make this correlation ourselves. Which is the decimal number of 75 in binary and hexadecimal? If you like, pause the video. If you chose number 2, you are correct. Let's add it up. B, which is equivalent to 11 in hexadecimal, times 1 is 11. 4, which is in the 16s place, 4 times 16 is 64. 64 plus 11 is 75. Let's go over to binary. 1, which is in the 1's place, 1 times 1 is 1. The next one, which is in the 2's place, 2 times 1 is 2. And that gives us 3. The next one is in the 8's place. 8 times 1 is 8. 8 plus 3 is 11. The next one is in the 64's place. 64 times 1 is 64. 64 plus 11 is 75. And that is a quick overview of the decimal, binary, and hexadecimal notation systems.